Okay, so thank you all for being here. Such a marvelous day. It's raining now. Let's try to go over the multi-cycle implementation and do as much as we can. Maybe we'll finish, maybe we won't. Who cares? Okay, we have today and tomorrow to do that, and on Monday. Next week I'll be gone 2 days, Wednesday and Thursday. Okay. Now, we did talk about the multi-cycle implementation last time. We all recall that I kind of talked a lot in the beginning, and then the slides didn't exactly budge with what I was saying in terms of the order. Everything was correct in the slides and what I was saying. So I'm thinking it's best for me to just redo this part again so we make sure that everybody understands. So, long story short, when we did the single cycle, we derived the implementation. When we're going to do the multi-cycle, because time is of the essence, I'm going to show you the implementation of the data path and then explain why it actually works. Now, long story short, the multi-cycle implementation will take multiple cycles to execute every single instruction. This table describes what's going to happen in those cycles. It has rows which represent the steps of instruction execution. So time here is going to go from top to bottom for every instruction, then you keep iterating. The multiple columns, one per instruction, supposedly. Some instructions appear together because structurally they do the same thing. The only thing that changes is the operation of the LU. Okay. Now, first two cycles are identical for everybody. They're the fetch and decode. Okay. Now, so let's start with one instruction. Here's the data path, and let's see how we can do the add. Okay. Now, we're going to do first the naive implementation, and then we're going to explain how we get down to the cycles I have at the beginning. Notice that the naive implementation at the end is going to end up with 6 cycles. Let's overview the cycles and let's see how they're done. First thing, cycle 1, we're going to fetch the instruction and keep it in some temporary register. This is because it's a multi-cycle implementation. We have some staging registers across the cycles. These are not visible to the programmer. These are what we refer to as microarchitectural registers. That is, they're not visible to the programmer. They're just to facilitate implementation. The programmer can never access them. IR, instruction register, was one of them. First cycle, I read the instruction. Second cycle, I just look at it and say, you're a lovely instruction. What are you telling me to do? Third cycle now, me being the control, can now decide what exactly needs to happen. So we're going to read the 2 registers. Then cycle 4, we're going to add them. We're going to write the result back to the register file and increment the PC. So let's see how these are done. And then we're going to make an observation. This we can easily stuff on the first cycle. This we can speculate and stuff it on the second cycle. This is what I did very hastily last time and confused things. So let's start with this simple way of doing things. Here we always take an action after we're sure it's the right thing to do. That's the whole point here. So let's go back now. Back, I said back. Okay, let me grab my stylus and highlighter. Okay, wonderful. Now, pen. Okay, cycle 1. Let's see how we can read something from memory. We take the PC through this path, and it becomes an address. We go to memory, and we say memory read, and then we load into IR. Everybody can see that the data path can do this. Again, we're talking about the data path now. The control will have to tell to the data path, do this. Yeah, cycle 1. Cycle 2, decode. The control is just looking at this. And maybe these two, but this is add, so it's not looking at this stuff right now. And it decides what to do next. Cycle 3, we are certain now this is an add, so we got to read 2 registers. The register names come from the instructions, so the upper 2 bits go through here and become a name here. The next 2 bits go through here, become another name. We read, remember this is combinatorial action. We read, we get the result at the end into R1 and R2. Now, this is a very unfortunate choice of names, R1 and R2, because they are identical to the names I used to identify the bits. It was not intentional, but I never got back to the point to actually fixing that because that would mean changing a lot of figures and stuff like that. As a side effect, I can claim that this is a nice way of treating you, of exposing you to the realities of life. Life is never fair, and sometimes you'll get this kind of confusion in manuals, right? People will use the same acronym or name to refer to two different concepts. It's upon you to understand what the heck they mean. I'm just telling you though, these R1 and R2 now are these registers, as opposed to the register name fields here. And we're supposed to understand this in the context that we're discussing. So far, so good about cycle 3. All right, cycle 4. Now we have these two values here, and we perform the calculation we want. We need to ship one of them as one input, the second one as another, and tell the LU do an addition. At the end, we're going to update the LU out and the 0 negative flags. Notice we do not update at the same cycle the raster file because the assumption is that the amount of time it takes to do this addition and pass the results there, and the amount of time it takes to do the raster file write are very similar, and if we were to pack them together, we're going to make the clock cycle twice as long. The assumption here is that at the end, the implementation is going to be such that this is going to be, maybe this is part of the critical path, maybe this is part of the critical path, but if my period is this, these are very close to the period individually. If we were to try to accommodate them in a single cycle, which you could if you wanted to, it will make the period twice as long. The CPU almost twice as slow. Can you see that from the diagram? No. You've got to make some assumptions. Okay. By the way, this is a fair assumption. It's not like just a random thing we're doing here. This is a fairly reasonable assumption to make. So we're in cycle 4. Cycle 5, now we're going to take the result from here and ship it back to the raster file as data. We're going to get the first name as before and now ship it as a name of raster to be written into. We're going to write, and now we update it. The register R1, where by R1 here I refer to the 2 bits here which are register name. Any questions about this? I see it in your eyes, you're all super excited about this discussion. And now we go to cycle 6, and we have to say to the CPU, you're done executing this, maybe you should go look at the next instruction. Nice thing, I have the PC. I can send it to the same ALU I used before to do the addition of the data. I can ship a 1 over here. I can say, please do what? I get the result back and update the PC. Okay. Notice I am happy to do that in a single cycle. Why? Because I'm not updating a register file. I'm updating a single register. So whether I do PC directly or whether I do the ALU out directly, it's identical for all practical purposes. What's not identical is the distance I have to travel, but let's ignore that for the time being. That's why I'm doing cycle 6. So far, so good? Any questions about the whole operation now? All right. So we executed the add in 6 cycles. Well, one thing you can do is you can look at the data flow dependencies, the data dependencies. Data dependence means the following. I am producing a result that somebody else needs. Okay. So let me show you one such dependence. Here, for example, we're producing R1, and this operation needs R1. If we want to make sure that we always calculate the correct result, we got to do this after that. Correct? Now, that's not exactly a data dependence that's visible to see on this diagram, but I got to see the instruction before I decode it, obviously, right? How can I decode something unless I have the bits? And also, I cannot use these bits before I decode, before I get the instruction. And also, if I want to make sure that this is correct, I have to wait for this. You write my spaghetti graph now?
Sorry, what's RF again?
That's the file.
So
it's the box. It's the box, right? You go, it's a box. Okay. Now, in order to write LU out to the register file, I need for this to be produced, and then I can write that. If I do this kind of thing, you'll notice that there are no arrows going to this guy. Okay? So I'm just showing you a semi-formal way of identifying parallelism in these actions. We wrote this in a logical way that kind of makes sense for a human, one step after the other. And then I told you, look at now at the dependencies among the various tasks, and let's try to find tasks that are independent. So we just realized that this thing is independent of the whole thing. The only difference is I'm using a PC here, and that guy is using a PC. So I better make sure I don't clobber this before that other guy uses it. So I hope now it becomes clear that you can stuff this all the way up. And that's what I did when I first described this. So we don't have to do this in cycle 6. We can do it here. We can say PC equals PC plus 1. Okay, fair enough? Yes?
That's only because we're doing like an add, right? If you're doing a branch, like can we still do this? Or
Yes, because we had the foresight when defining branches to making sure that this is a common sub-expression to both target calculations. Because even when the branch is taken, it's PC plus 1 plus something else. So this is useful regardless. This is now software hardware code is actually, instruction set and hardware code design. You're saying it would be nice to define the instructions this way so I can play this trick at the implementation. And these are important things to do because you can easily simplify hardware by just writing an extra line of on a book. That's all there is. You spend a few pieces, just write a bunch of letters and you're done. You can make your hardware simpler. And because it's not people actually calculating the distances, for branches, there's zero cost to this. Fair enough? Now, next thing is, notice that I drew this is a very nice arrow. I drew this arrow saying that if you want to make sure that always you read the right values from the register file, you got to wait for decode. And I'm choosing my words very carefully. I'm saying if you want to make sure. Okay. Now, as I said last time, I'm repeating myself a little bit here. There is a class of optimizations you can do in hardware that say the following. There are some actions that it may be good to take proactively. That is, without waiting to make sure that this is correct. So this is what we've done last time. We hoisted this, I think that's the technical term, into the second cycle. And we said, we think that's going to be a good thing to do. How about we do it? Because this is an add now, this is a good thing because it's actually useful. But it's not always useful. When something is not useful, the next question is it harmful? Does it change state? These are reads, they don't. By the way, parenthetic note, there are cases where your CPUs will take actions that are harmful, that is, they will change state. In that case, they save around enough so they can clean up after themselves. They make a mess, they say, oops, sorry, let me clean it up and present to you the way it was before. There are ways, we're not going to see any of this right now. Are we okay with add? All right. I think last time we said subtract is identical. Great, we've done that. None is the same. Great. And then I think we also did this, but let's again review because this is important. I mean, we have to be on a solid foundation here. I mean, that's one of the most important parts you're going to learn in this course. Let's do the ORI. Right? ORI, again, if we look at how we're going to implement that, let's see how many slides I have for this. Okay. I'm supposed to be using different colors now. Okay, I'll try to do that. I hope you all understand that up to cycle 1 and 2, we're going to be identical to everybody else. So cycle 1, we're going to fetch the instruction, read it to IR. Cycle 2, because we're speculating, we say let's use the upper 4 bits to read 2 registers. We're going to read 2 registers here. Do you want me to draw this? I will assume that you don't. If there was a yes? Okay. So there is a yes, so let me draw it. Cycle 1, I'm doing this. Okay, this is 1. Cycle 2, I am doing this. And these have to be identical for all instructions in this implementation. We go to cycle 3 now. We just realized this is an ORI. And we also realized that the registers we used are not useful. We've got to go and read K1 so we can do the operation. Again, for this, we have to go back to the definition of the instruction. It says, notice after decode, it says read K1, where K1 is a specific register. So we got to go now, and in cycle 3, we have to do the right thing. So let's pick another color. Ooh, this looks nice. Okay, so now we're going to take this, the number 1 here. Can you see that, the magenta? Okay. And we're going to read this. By the way, the register file, parenthetically, still reads whatever you give it here. It's okay to keep giving it junk because reads are not destructive operations. So it will still read using those 2 bits another register, but who cares? That's okay. So this is going to be cycle 3. The cycle 3 amounts to read K1 into R1. Now we go to cycle 4. My apologies to people that are colorblind now. 4. This is supposed to be red, so I'm going to make it bold too. Sorry, green. Okay. So I take this thing. That's the first operand, which is K1. Now I need to take immediate 5 and 0 extended. It's this path down here. Yes. And this goes in here. Wonderful. And I say to this guy, do an OR, please. And at the end of the cycle, I will update this guy and these guys. Fair enough? And that's cycle 4. That's a nice 4 there. Cycle 5. I'm running out of options here. Okay, hope this shows. It's going to be this thing, go back here, take 1. Notice I'm taking this one and write. Fair enough? And that's cycle 5. And everybody okay with this up to this point? Well, there's a minor bug here, which I should have done in cycle 1. While reading the instruction, I should have also gone to the ALU. I should have said +1 and updated the PC in cycle 1. Sorry for that, I forgot about that. This is ORI. ORI is going to be the longest instruction. Why? Because it uses a completely different way of specifying what are the source operands, which is not structurally identical to the other instructions that do use operands. And because we speculate in cycle 2 that it's better to use the register names from the instruction as opposed to K1. If you wanted to do a real architecture design, well, you take programs out there, you measure statistics, and you say which of the two phenomenon is more common, because you want to optimize for the common case. If in the unlikely case, ORIs are much more frequent than the other instructions, you can change cycle 2 to read K1 directly. Speculate that's a good thing. Right? And there's crazier things you can do. There's this, you can build hardware that actually tries to guess whether the next instruction is an ORI, whatever. Anyway, you can go down that path at some point. I'll shut up about this. Any questions? Loads. Loads, first 2 cycles the same. Cycle 2, we're going to be reading R1 and R2. Only R2 is going to be useful for us, which is good. Half of the things we've done are useful. We're going to go to memory, read a value, and put it back in. I think we talked about this last time too. Let's talk about that. Let's start. So cycle 1 is the same as before. I'm not drawing that. So, not because I don't want to. I don't think it's interesting. Cycle 2, I'm reading 2 registers, so I have this and this. Out of those, R2 is useful. So we're taking R2 now, and we're going through this path to memory as an address. We're saying memory read. At the end of the clock cycle, we get the data out, and we load it to another staging register. So if you wish, this serves the same purpose as ALU out, but for a different unit. You can view this as one blob, that's another blob. These are both expensive things in terms of time. Anytime you access an expensive thing and you have data that you need afterwards, you put a staging register. I have one register here, call it banana, and I have another register here, call it kiwi, right? MDR and ALUR. This is a very good name, memory data register. That's a very good name. Okay, so I'm staging it there. So then, in the next clock cycle, which is going to be cycle 4, I can take MDR and I can zip it back to the register file. That's all there is to this. So we're going to take this guy, zip it through this path back to the register file, pass the R1 name as a register name to write to, RF write, we're done. 4 cycles. Fetch instruction, decode and read the registers, read memory, write back to the register file. Stores, this is going to be 3 cycles, because we're going to read the instruction, decode and at the same time read R1 and R2. So these are going to be fused together in time. Both are useful. One is address, the other is data. Cycle 3, we write it. So let's just look at cycle 3 now. We're here, we just read this in cycle 2. Both of them are useful. One of them is going up as address. The other is going down as data. We say memory write, done. End of cycle 3, we're done. Fair enough? And now we're almost done, believe it or not. That's the nice thing about talking about similar machine because we can focus, look at the whole thing. Let's do branches. We're doing this, and then we're doing that. During that cycle, we're looking at whether we need to update the PC or not. Notice the definition. I think that goes back to your question. Common, common. This has been hoisted in cycle 1. So now we only need to do this. You can design your machine so that it only takes a third cycle only if it needs to. Or you can make it so that it always takes a third cycle. It's up on you. I think in the diagrams I have after that, I always take a third cycle just because. So in cycle 3, there is nothing to this. Let's look at the data path. Again, cycle 1, cycle 2, identical. We read 2 registers. They're useless. So there is something here. And there is something there, but we don't need it for the branch. Cycle 3, what we're doing is the following. We take the PC, if need to, take the immediate 4, sign extended, pass it to the second operand, do a plus, get the result back and update the PC if you need to. That's all there is to it. Whether you need to or not depends on these guys and the opcode. That's it. Done? Forget about that. Alrighty then. What is this? Do you have any questions about this? I mean, alrighty. Now we have half a CPU here. And you know, for these things, half means you have nothing because it doesn't work yet. We need the control. We have the puppet. We need a person to play the puppet. Okay. This collection of egg thingies, does it mean anything to you? Does it look like something you've seen before? Can somebody help me here? Flow diagrams. And what do you say?
The sequence of control for each of the instructions.
Yes. Okay. You guys did digital design, right?
Like an FSM.
Yes. Thank you, sir. That's bingo. That's a final state machine, right? And it does translate into when you build final state machines, you do use truth tables that map current state to next state and the function over there. So what you have here is a final state machine that describes what the machine should do since it's a CPU. Remember, a CPU is a loop. And if you notice this, there is this thing. This is supposed to be green, by the way. This is in the beginning of time, you woke up and you were a CPU. How's life? Well, you go here. Guess what? Next step, you see an arrow, do this. After that, oh, by the way, that's going to happen to be decode. Now you know what is the instruction you're looking at. Notice that there are a lot of things going out. You're going to follow one of those paths. So it's a little bit more interesting to be a CPU. You follow, but these are the choices you have in life. You're going to follow those paths. And notice, let's follow one of them. You go down here, that's cycle 3, cycle 4, and life is not that interesting after that because this is an arrow that takes you back to green, and you're not the wiser anymore. It's as if, oh, you woke up and your CPU, PC points somewhere, just fits something. Okay, so that you understand what's going on, here's the following. This is color-coded. This is cycle 1, cycle 2. These are blues. They're all cycle 3. Where needed, there is a cycle 4. And remember, there's one instruction that needs cycle 5. Cycle 5. Fair enough? Now, first 2 steps are common to everybody because you don't know the instruction yet. From cycle 3 on, you differentiate. What you see here is add, subtract, NAND, which are structurally identical. The only thing that changes is the LU op. Right? This is shift. And by the way, I think I could have merged that here too. But anyway, it's there to confuse you. Because all it changes is the control signals. But it's not exactly structurally identical because you're using a different path to the LU. But I think we could have been over here. Let's forget about optimizations right now. Let's say this is the cycle 3 for shift. Notice that they have a common cycle 4 because it's structurally identical for all of those instructions. You write back to the register file the result of LU. That's why it's the same. This is ORI. Different cycle 3, 4, and 5 because it has to do different things. This is the load. This is the store, just 3 cycles. These are the branches. Again, I do not want you to approach this as, is this the best possible final state machine for the control? I want you to approach this as, is this a final state machine that works? It does the right thing. Now, just to remind you a little bit from final state machines, these are states, and every cycle you're supposed to cycle through those states according to the arrows and the rules they specify. If you don't see a rule, this means you just go. Next cycle you move around. So in the beginning you're going to be here, next cycle you got to be there. Notice in these there are arrows there. This is meant the instruction is this, which means the IR has a particular opcode there. And after that they're unconditional again. Fair enough? Inside every state there are values for the control signals. I don't know if you can see those. I can barely see them myself even though I'm next to it. But if you were to go through this, you're going to see this says PC write, address select, memory read. These are the control signals. These are the connections that go into the data path that tell it what it should do. So here we have a way of expressing what the data path should do per step and according to the instruction type. So that's why this is the control of the machine. We're going to use that to build a final state machine that implements the control. That's it. This is different than the single cycle, which was just a combinatorial circuit that produces that. So another way to view what that final state machine is, this is that. So the way I derive that particular diagram with the blobs and the arrows or whatever, I'm basically looking at this table. That's what it means. It says this is the initial state. Time flows like that. So think of this having arrows going downwards per column. This spans all columns, so it's one arrow. Here you have multiple columns, so you're going to have multiple arrows. And then inside each one of those states, rows, I have an action that needs to happen. In the previous diagram, this is translated into plain binary signals. This is more high level, more human-oriented description. So there is an arrow going from here to here. There is an implied arrow going from here, 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 which depends on those variables. That's the way to interpret that, and so on and so forth. That's what we're doing. Now, just a description, a reminder for what final state machines are. This is one type of final state machine. There are different types. I think 2 of them you learn. You learn about Milli and Moore. Those mean anything to you? The difference is whether the current output depends only on the current state or the input as well. And I don't remember which is which, honestly. I forget myself. Because they're just names. That's the concept. Okay? Now, what do we have here? What's going to be the control? The control is going to be a piece of logic with another piece of logic combined, but you can view this as one big blob that takes as input information from the data path. In the particular case, it's going to be the instruction register, and we only care about the last 4 bits because when I look at those, I can tell what instruction I'm looking at. For some of them, I need to look at 4, 4, 4, actually for most. For a few of them, shift and ORIs, I need to see only the 3. So this is input. That's one of the inputs. The other is I need some way to tell what step of execution I'm in. Is this the green state in the beginning, or is it I'm step 2, step 3, step 4, whatever? So that is this thing over here. What this logic has to do, it has to do 2 things. It has to produce the signals for the data path for this cycle. Is this part over here. Some of those signals depend on the 0 and negative flags if this happen to be branches. Otherwise, they're just a direct result of this, right? And it also needs to sequence through the states. So for that purpose, to decide what the control signals should be, it has to look at 2 things. What the instruction is and what step I'm in. Right? So that will produce the control signal. So the control signals are going to be a function of IR, potentially 0 and negative if it's branch, and what step I'm in. That's why there's this input here. Furthermore, this has to implement the sequencing. So the other output of this state logic is what is the next step. This is an encoding of the steps. You remember this from final state machines? Your stance makes me think that there is something is hazy here.
A little hazy.
A little bit. We'll remember it eventually.
It's familiar.
Yeah.
So there are 2 things we got to do. The important thing to understand here is the following. We are going to have some state here. This is a register, by the way, that will allow us to uniquely identify what step we're in. Okay? Let's look at the, let me go back. I want you to understand this in abstract, and then I'll tell you the specifics. Now, how many different things do you need to remember here? What are the possible states you can be? It's how many of those blobs you have, right? Because you got to remember, I'm at this blob, so then you can go to that blob. You with me? Think of this like GPS coordinates, right? And these are corridors, whatever, rooms. I'm in this, or like RPGs with those rooms, like Diablo and stuff like that. I'm in this room, I can only go to that room after that, something like this, right? So I need to be able to uniquely specify its room. How many rooms are there? 14. Let's pretend I counted correctly. There are 14 rooms. How many bits do I need to specify 14 things uniquely? Good, 4, because that allows me to specify up to 16. I can fit 14 in them. So give me 4 bits. I can assign a unique identifier to each one of them. Does it matter which one I assign? No, any will work. The only question here is, will any particular assignment make my logic of transition a little bit simpler? But we're not going to care about that. So grab the numbers from 0 to 16 and assign 14 to these states any way you like. This is your control flow machine. So your control machine. You can do whatever the heck you want. Just assign numbers there. Okay. Let's pretend this is 0, 0, 0, and this is 0, 0, 1. You with me? Okay. So I'm going back to the final state machine now. This diagram over here. I want now a piece of logic. Give me a second to grab my pen. I want a piece of logic that will say the following. Here, the current state is going to be 0, 0, 0, and 0. Okay. I want the final state machine to do the following. I want the next state logic to produce what here? What should be the output for that input? It should be 0, 0, 0, 0, 1. You guys got it right. Because that's the transition I want to do. At the same time, I want the control signals to correspond to what are the actions that need to happen during that cycle, which is the following. How these are specified? Well, you read this, you hope and pray the lovely person that wrote this thing, that was me, they actually knew what they were talking about, and these are correct. By the way, don't trust me on this, right? And this may be wrong. Again, if you find any bug, let me know, because it might be just the simplest answer is the right one. You look at those and you say, these are what my control signals should be. Okay? Now, after that, let's say you find out that the instruction is an add. Then you go to this state. Does that make a little bit more sense? That's final state machines, if you grasp the key idea, they're very straightforward things in the sense that there's a combinatorial logic, and the only thing that makes it a final state machine is that the logic says, I will go there next, and there's a register in between, so that these transitions happen in steps. Hopefully this was a little bit helpful so that we can move forward now. So what we can do now is the following. We're going to say, look, I'm going to show you how you can come up now with this logic here. All right? So we're going to be going through various instructions and cycles, and we're going to say, well, for this step, this is what the control signals need to be. At the end, we're going to end up with a big truth table. Let me show you the truth table. It's here. And now you have to, I will have to squeeze it in here. We're going to have something that's going to have a bunch of inputs and a bunch of outputs. Again, sorry for flipping things all the time. But essentially, if you view this block in isolation, it's a combinatorial block that takes a bunch of inputs and produces a bunch of outputs. Some of the outputs are control signals. Some of the outputs are next state. Same thing for the input. So let's go to the diagram here. This thing is going to have current state. This is one of the inputs. There it is. Okay. IR. The parts hook here, 0 and negative. I don't think it has any other inputs. That's it. IR, current state, 0 and negative. These are the inputs. Okay. Are there many inputs? Probably more than we care as humans, but there are. By the way, we identified that this has to be 4 bits at least. because there are 14 states we need to care about. Okay. So we're going to have 4 plus 4 plus 2, 6. So it's not that bad, 64 rows. It's not a big table, but still a bit outside of comfort zone, I would say. Okay. That's why you want tools for that. What are the outputs? There are 2 sets of outputs here. One is, what is the next state? What should I load there? So notice there's a dependency between current state and next state. I mean, when you fill in this table, it will all make sense, right? You'll say, I'll go to the next row. And then all the control signals. As many as we have in the data path. This is from the data path. That's the truth table. And you're going to start saying, in the beginning, I was in state cycle 1. And you can give any number you wish to this. Any number. Doesn't matter. Then I go to cycle 2. Then you write underneath. This is cycle, and by the way, here it's going to be, I don't care, I don't care, I don't care, because this is, I'm just fetching stuff. Cycle 2 now. You're going to write something like this. It will say 001, but guess what? Here you do care. There's going to be stuff like this. If this is 0000, then you go to this state, which will be the cycle 3 of adds, subtracts, and nonce. If this is something else, like 0001, whatever, you're going to go to somewhere else, so on and so forth. I hope this kind of makes sense how the truth table will look like. So in the slides that come after this, I don't have this part. I have this part, the control signals. And the other one is implied. Any questions about this part? Are we ready to go through one of them? Because I'm going to do 1 or 2, and then I'll say, OK, the rest is up to you. Here's the final result. OK, so let's do cycle 1, cycle 2. So this is going to be the cycle 1. And we're going to see what the flags need to be, the control signals need to be, so to do that. Notice there's no discussion here about what the instruction is, because this is cycle 1. It's the same for everybody. That's why there's no, oh, this is for add or subtract. What do we need to do in cycle 1? Remember, it's written up there. We need to take the PC and read IR, and also take the PC, increment it by 1, and write it back. So first question to you. Now, our goal in life, fill in these signals down here. So these guys, we need to fill in those, OK? What should PC write? I hope everybody sees that we will update the PC. OK. What should be address select? Let's look closely at our diagram. Address select is the signal to this multiplexer that says where the address comes for to read or write to memory. It can either come from the PC or it can come from R2. So it has to come from PC. If you look at the way this is drawn, it says if you want it to come from PC, this has to be a 1. That's a micro-architectural choice. It's not visible to the programmer. So that's why this is 1. Great. Memory read. Are we reading from memory? Yes. We have great crowd participation, 2 out of whatever. So this is, yes, we're reading because we're fetching, absolutely. Now, are we writing to memory? No, absolutely not. Are we loading inside IR? We have 100% increase in participation. We have 4 people now. So IR load, yes. Are we going to read from the rest of the file? Oh, the rest, by the way, I forgot to tell you, the next signal is R1 select. R1 select happens to be the signal that controls this multiplexer. Are we going to read from the rest of the file? Everybody does this. No. And I think in here this means no, right? Okay. Yes. Good. We're not going to read from the rest of the file. Okay. Good. Do we care if we do read from the rest of the file? We don't care. So for that reason, if you want your design to be crystal clear, you can say, actually, you have to pick a choice there. So I don't care. I'm going to write the rest of the file. I'm going to spare you the drama. You're not going to write the rest of the file in cycle 1. What should be the input to the LU? The first input, LU1. 0 or 1?
0.
Huh? 0. Oh, you guys are looking at this the right way because I was looking at my red line. OK, 0. That's absolutely, I would have said 1 incorrectly. LU2? 0, 0, 0, 1. OK, that's a 6 or 1, whatever is that. OK, 0 or 0, 1. We want to pass the 1. I'm talking about this. What should be the ALU up? And, which I think is 0, 0, 0, but let's say plus, and we go look it up. Oh, so we write to the ALU out?
Yeah.
No.
No.
No. Does it mind?
No.
It doesn't. But because it doesn't, any answer is correct. Your design will be correct, period. What should be the name of the register that we're going to send to the register file to write to? By the way, this is a thing, as I said this before, a lawyer will say to you. Because it has a baked-in assumption that you will write to the register file, which you want. So be careful when answering questions like that, because they want you to answer them in a way that will say, aha, so you're writing. So anyway, what should be this?
Doesn't matter.
Doesn't matter, because we're not going to write to the register file. Are we going to read something from memory and load it to MDR? No. Do we care if we do?
Yes.
MDR is this guy?
Oh, no.
No? Okay, yeah. I mean, there are two choices now. We don't care whether we're going to change this guy. We could have written 0 if you want to clear. Are we going to update the flags? Absolutely not. And we do care because it's architectural state. We shouldn't change it at random places, only when it is. Are we going to change these registers? We don't have to. Do we mind if we do? It's cycle 1. No.
Where is ALU right?
What?
ALU right.
Oh, yeah, sure. It's here.
Oh, it's that. Oh.
Yeah, yeah. Somewhere at some point, it should have been there, but it's not. But that's what it is. It should be ALU op right. We're good? Got it? Okay. You can do this now on your own. I have faith in you. Let's do one more. Okay, fine. We have a little bit more time. Now we go to next state. Okay, before there's no question, it's like a single transition. You go to whatever you call the second state, you put that pattern as your output. In this table, I put 0, 0, and 0, 1. Right? But it could have been anything you want as long as they're unique. Let's do cycle 2. Now, what do we have to do? We have to do these things. This is our blueprint now. This is what we got to do. It's going to be super exciting. Are we writing to the PC? No, we're not writing to the PC. We're just doing this. Do we care what goes into memory as an address? We couldn't care less. Are we going to read from memory? Actually, you could have said X there, but don't do that because let's say it's expensive. We're not going to read. We're not going to write. Are we going to change the IR? No. We want IR to stay put so that, okay. Do we care what register name we're going to send to the register file to read the first register? Yes, we do. Where should it come? Should it be 1 or 0? 0, according to the choice we made on how we're going to speculate. Should we write the register file? Nobody's going to like us if we do that because the machine is going to be doing random things. So what's the operand that we should send to the ALU? The first operand.
Doesn't matter.
Yes, X is your friend. Doesn't matter. And it doesn't matter. And what should the ALU do? We couldn't care less. Should we write the output register from the ALU? Why not? It's there and we don't care. At this point, we haven't written anything to it. Should we care what name we send to the register file? That's a leading question, by the way. Should we care what the name is to the register file that it's going to use to write something? This thing? We don't care because guess what? Somewhere here it says RF write 0. So you could have sent anybody standing in front of the door. You're not opening the door. So we change MDR?
Doesn't matter.
Yeah, sure, why not? Change the flags?
No.
No. Should we change R1 and R2, these two registers?
Yes.
Duh, I mean, come on. I mean, that's the thing that we want to do. I mean, there's only so many we got to do. That's the one thing. Everybody happy? I mean, with this, not in general. I'm not quite sure I can help you with anything else. Not sure I can help myself either. I'll be happy to discuss, but nothing to do with this course, though. Fair enough? Okay? Ta-da! You keep doing this, you're doing that, you're doing this, you're doing this, this is wonderful, this is very fun. You keep doing it, you keep doing it. I wonder if I have anything at the end. I do have something, which, by the way, it's an interesting discussion. Of course, otherwise, why would I have it there? But let's do that tomorrow because we only have 2 minutes and I don't think I will do it justice. If you wish, this is good practice for you. How about, I know you have nothing else to do with your lives, absolutely, especially with courses. So, but if you wish to use this as an opportunity to learn something, because people, I mean, myself, I learn a lot from my mistakes, not from the things I understand easily. So try this. You want to change the data path and the control to implement this new instruction now. This is a load, which addressing mode is not a direct register. It's what's called post increment. There are machines that are there, so it's an opportunity to introduce you to this addressing mode. What this thing does, the definition of it is the following. Do a memory load as you would otherwise, but treat R2 as a pointer to memory, which it is, and increment it by the size of the data you're accessing. This looks like a pop from the stack. It also, when you're copying strings, this is copy, read data, increment to the next character. Same thing when you write. So that's why the post increment addressing mode sometimes is implemented in machines. There are machines that do have this. ARM, for example, I think has it. Okay. Now, this is a blueprint. Go back to the data path and see what needs to change so you can implement this. And let's do this tomorrow together. Of course, I have the slides, I think, posted, so you can go look at what needs to happen. Do yourself a favor and try to do it on your own. Okay. Again, because I think thinking about this will help you understand the data path, because you have to understand what's going on to be able to reason about what needs to change. Making a mistake is going to be golden, because then you have to go think again, what did I do wrong and why? And that's then you're going to understand everything. I think that's the, and unfortunately, because we don't have a textbook, okay, that I'm saying we're following exactly, you don't have that many opportunities to play with this stuff. Okay. So as always, thank you for your time. If you wish for me to review your midterm, I'm happy to do so. Please make my life as simple as possible. Follow the instructions I posted on the website. Again, this is, think of it as making your case in front of a court, right? You're saying, this is why I deserve this, and this is what I should get. Right? Don't think about, I mean, what's the worst that can happen? You get a no, right? So what? I mean, it's not as if I'll remember this for the rest of my life, or somehow it's going to influence anything else. Just don't say anything about me or my mother or anything like that. You don't need to say that. Nothing. Just keep it technical. Okay?